All right, we're going to go ahead and finish up 3.2 now. So let's take a look at this here. Differentiable on an interval and one-sided derivative. So here, a function function y equals f of x is differentiable on an open interval, finite or infinite open interval, if it has a derivative at each point in the interval. So that means that in some interval in here, every point down here on the graph you would go through on this interval between a and b, every point would have a derivative. Now, we can have a closed interval. It's differentiable on a closed interval if it is also if it's differentiable at the interior points, and also basically what this is saying has these limits. It's also differentiable on the endpoints. Okay, and so that's both. That should be both for a and for b there. But basically, we can do the derivative of it there. There's a limit, a left and right limit for each endpoint. Okay, let's take a look here. Let's show that the function f of x equals the absolute value of x is differentiable on negative infinity to 0 and 0 to infinity. And those are open intervals, okay? But it has no derivative at x equals 0, which is why we have the parentheses here, these parentheses, instead of the brackets, because we cannot do the derivative there. So let's take a look. So the graph of the absolute value of x is this V-shaped graph. It looks like this, right? That's the absolute value of x. And so if we want to do the derivative of the absolute value of x, first thing we can do is the derivative on the negative side. And so that's going to be the derivative of negative x, okay? And when we do that derivative, if you do the whole thing out, what you're going to find is this just equals -1. In fact, you don't even really have to do the whole thing out because it's simply the slope of the graph. We know the slope of that graph is -1, right? Y equals mx plus b. In this case, b is 0, and m has to be -1. That gives you -x. All right, on the positive side, the derivative of the absolute value is just the derivative of x. And it has a slope of 1, so the derivative there is just going to be 1. So on this left side, we can do the derivative anywhere. We'll get a -1. That's the negative infinity to 0. This is the right side. This is the 0 to infinity right there. And then basically that gives us a derivative function, f prime of x equals, and it's going to have to be piecewise here. It's going to be 1 from 0 to infinity, and it's going to be -1 from negative infinity to 0. Okay, and if we graph that, if we actually graph out f prime of x, right, so this will be f prime of x. This one was f of x. Okay, this f prime of x, what we're going to have is nothing at 1, so open circle, and then this is at x equals 1, and then -1, open circle, and we have this going this way. And we don't actually have anything at 0, therefore we have no derivative at x equals 0. And if you think about it, if we zoomed in on this little corner right here, right? We zoom in on this corner, it's a corner. And when you have that corner like that, where's your derivative? Where's your tangent line? Is it tangent like this, like this, like this? I mean, we can draw a ton of lines that hit that corner in just one spot. So get rid of that kind of. Anyway, that's what we'll have right there. Next, we're looking at some examples of derivatives at a point where it doesn't exist. And this is what I was talking about, the sharp corners and things like that, where there's really nowhere to put anything. So, at a corner or a cusp, those are places where we're not going to be able to take derivatives because it needs to be smooth and continuous. Next, some more examples here. If you have a vertical tangent here where the slope of PQ approaches infinity from both sides, we're not going to be able to take that derivative because we're going to basically be dividing by 0 when that happens, just like we had undefined for vertical lines. If there's a discontinuity, if the graph is actually broken between 2 points like that, then we can't take a derivative there either. And there's 2 examples shown here is another discontinuity right there. Okay, so that makes a pretty big difference. So thus, differentiability describes smoothness. You need it to be smooth and continuous in order to take a derivative of it. So if something is differentiable, then it implies continuity. If f has a derivative at x equals c, then f is continuous at x equals c. Okay? And does continuity, though, is that the only thing that implies differentiability? Well, no, because if you look at this crazy graph here, every little point you move is going to be changing all over the place, and you're not going to be able to take derivative on those things. Okay, so that's pretty much it. We finished this up, nice short video, and we'll continue on in the next section after this.